Hello everyone, thanks for tuning in. My name is Ashwin Pananjady and I started on the faculty at Georgia Tech earlier this year. Today I'll be telling you about a space we've been exploring at the intersection of statistics and optimal control, trying to uncover the instance-specific difficulty of reinforcement learning problems, and then to use this to guide algorithm design. Now, given the time constraint, I won't get super detailed into any particular result that I'll present today, but my goal is to give you a flavor for what's interesting to study here. So broadly, reinforcement learning is this influential paradigm of decision making under uncertainty. It's seen a lot of applications ranging from control-based simulation to mobile health. The particular facet of reinforcement learning that's relevant to this talk is that there are many algorithms to do reinforcement learning. So here's just a partial list, a screenshot from Wikipedia. And trust me when I say it's partial. And all of these algorithms, the reason they all exist is because each has a variety of behaviors in different environments. So the goal of today's talk, the high-level question that motivates us, is can we explain this variety of behavior and establish problem-specific baselines or environment-specific baselines of difficulty that can then help us evaluate different algorithms, reason about optimality, design new algorithms, etc. Now, given that this is a question at the intersection of statistics and optimal control, let me set up just some basic background from both of these disciplines. The view from statistical decision theory first. We have a parameter, observations from a probability model, and we have to estimate that parameter. We would like to incur small error measured by some loss function, and the expectation of that loss function is given by the risk function. Now, it's important to note that each estimator has a risk function, a risk profile, as a function of that underlying problem instance or parameter. And it's not always easy to use these risk profiles to reason about what is the better estimator. Standard ways to do this are to sort of scalarize the risk using, say, the worst case notion or the Bayes notion. But what we will be interested in this talk are local notions of risk, somehow classical in the statistical literature, is what is the optimal risk function itself? Can we understand the landscape of this? Because that's what measures local adaptation. How difficult is a particular problem instance or parameter theta star to estimate, right? Now, the second bit of background I have to give you, given that this will be applied to reinforcement learning, is from optimal control. So reinforcement learning is about learning in a Markov decision process. What's a Markov decision process? It consists of a state space and an action space. When you're in a particular state, you take an action and transition to the next state randomly according to some transition kernel. While you do this, you also accrue some reward for that state action pair. So you do this again and again, and the goal is to maximize your long-term reward. In this talk, we're going to consider the infinite horizon discounted notion of long-term reward, where this is a discount factor gamma, some number less than 1, that sort of conveys that immediate rewards are more useful than further along the line, right? So the problem is, as phrased about taking actions, turns out can be reduced to just reasoning about good policies, which are essentially maps from states to actions. Given a state, what action do I take? Now, a value function of a policy basically measures the long-term reward that policy accrues from some given initial state x. So this is now a function. If you have d states, it's a d-dimensional vector. One important thing to keep in mind over the course of this talk is some notion of effective horizon will keep appearing. So this is a number 1 over 1 minus gamma. As gamma goes to 1, the problem gets more and more long-term. There are more terms in this sum, if you will, so it gets more and more high dimensional. So this is a natural sort of dimension in this problem that will appear again and again, so keep that in mind. So far, I've only really described MDPs. What's reinforcement learning? It's the problem of finding the optimal policy. What is an optimal policy? One that has value function that's the largest uniformly for all states, and such a policy exists under mild assumptions. Can you find such a policy with access to samples of transitions and rewards? That's the problem of reinforcement learning. Okay, now a standard way to do this is to do what's called policy iteration. Start at some policy, evaluate its value function, improve that policy according to that value function you just evaluated, and then move to the next policy, evaluate its value function, etc., in a loop. So clearly a key piece in this is the policy evaluation problem. Given a policy, what is its value function? And today, rather than study full-blown reinforcement learning, we will study policy evaluation. The problem of given samples from that transition kernel and the reward function, can you evaluate the value function of a fixed policy? And in particular, can we reason about adaptation in this process like we set up a couple of slides ago? So let me discuss the setting here, which is reasonably simple, much simpler than before, because things only depend on state since the actions are fixed by your policy. So in the setting with D states, we basically have a Markov reward process, a chain with transition matrix P, this is D by D, and a reward function of vector, which is just a D-dimensional vector. It tells you what reward you get in a given state. So we're interested in finding the value function, which can be shown to satisfy a very nice system of linear equations here. So this is also a D-dimensional quantity, and we want to find it from sample access to P and R. So how do we define sample access, the observation model? Today we're going to use what's called the generative model. So effectively, what's a generative model? There's a simulator. If you put in a state X, it will give you a sample from the transition kernel given by that next state, X prime, and a sample from the reward function, capital R of X. Okay? So this is a useful sort of simplification of the problem, goes back to the 90s, and it's been very useful in RL to decouple various issues. So this is going to be our observation model for the moment, and I'll set it up in a little bit more detail later, but we're going to assume simulated access. And the goal is to estimate the value function, V star, from observations of the transition and reward that come from this simulator. Possibly with function approximation. So sometimes when capital D, the number of states, is massive, you might want to not necessarily find V star, but just the best approximation of V star within the span of a fixed set of basis functions. So this leads to two questions, which will form the two parts of this talk. First is the question of estimation, right? Which algorithms adaptively estimate V star in this problem-dependent sense? And the second part is the question that relates to function approximation. Again, what are the local fundamental limits of function approximation, and do they look any different from the way we usually think about, models and approximation and model selection in statistics? So let's dive right into the first question about estimation. And to do this, we have to, describe the concrete estimation problem and also the algorithms that we'll evaluate in some instance-specific sense. So it's convenient, first of all, before we do anything, to actually view this value function estimation problem as finding the fixed point of an operator equation. So this value function here can be written as the fixed point of the operator t if t is equal to r plus gamma p. So that's just something to keep in mind. It's going to come up again and again over the course of this talk. The concrete observation model that we will study policy evaluation in is essentially the IID observation model, where we get IID observations of P and R, capital N of them, where N is our sample size. So each of these observations could look like this. You basically see a transition from every possible state simultaneously and a random reward also from every possible state. Now, clearly you can generate this from that simulator, and this is going to be our setting. What we want is an estimate V hat that's good in L infinity error. So L infinity error is going to be the metric we care about, and this is motivated by policy iteration. We will do other things just shortly, but for the moment, think of the L infinity error. Natural estimators here, well, the plug-in estimator. Just take your samples, average them, plug them in to this Bellman fixed point equation, find an estimator. Other estimators that are more sequential are based on stochastic approximation. For instance, the classical temporal difference learning estimator is a sequential algorithm that at every step takes a convex combination of the current iterate and mixes that in with the sample Bellman operator, something that's an unbiased estimate of the Bellman operator evaluated at the current iterate. Okay, so this is going to converge to the fixed point under some assumptions, or say on the step size there, alpha k. So one thing you can do to lend stability to stochastic approximation is to average your iterates. This is classical. It goes back to the 80s and 90s. Great. So those are the three algorithms. They've been defined. They're natural algorithms to study here. One thing that is common to all of these algorithms is that the error of these algorithms will decay with n, the sample size, as expected. But it's not just dependent on n. The sample complexity, the number of samples you need to get epsilon error, will depend on other problem parameters. For instance, the discount factor or the discount complexity, 1 over 1 minus gamma that you see right here. Now, the sort of minimax or worst case approach to study these problems will ask what is the worst rate of change of these curves as a function of gamma over the class of all, say, bounded MRPs, right? This is a valid question, but it can often be very, very pessimistic, this prediction, because different problems may have completely different behavior. Now, in the next few slides, I will flash plots that instead look like this, schematically speaking. On the x-axis will be some distillation of the easiness or the difficulty of a problem, which clearly any minimax or worst case bound cannot capture. What we will see is that these algorithms actually exhibit some adaptation to easiness. They get smaller error for easier problems. And to understand this, we will prove local lower bounds that actually narrow down and think about instance-specific difficulty of these problems, right? So this already suggests where we're going. It'll help us delineate the behavior of different algorithms based on whether or not they attain this instance-specific baseline. All right. So the next question is clearly, for this problem, how do you actually capture instance-specific difficulty? What is the functional that matters, and how are we even going to measure this? So in standard minimax risk, we typically look at the worst case risk of our problem over the entire space, right? Or worst case risk of an estimator, and ask for the estimator that minimizes that worst case risk. Well, the local minimax risk is defined very similarly, except now you take the worst case over a local neighborhood around a particular problem instance of interest, in this case, P, R. So we're going to scale our risk or loss function by root n to actually get at the problem-specific parameters. And this is just a convenient normalization. Of course, all the standard sort of interpretations of minimax risk still apply. We really want the worst local model now instead of the worst global model, and the best estimator for that model, right? Okay, so you can get different notions depending on how you define this local neighborhood. In the asymptotic sense, as n goes to infinity, it turns out that it suffices to define the local neighborhood as instances that lie within a 1 over root n radius of the instance of interest P, R. We call this LC of J, and this is really the foundation of the celebrated LAM theorem that goes back many decades. In the non-asymptotic theory, it turns out to be more convenient to define the local neighborhoods as a 2-point family. So an instance I in addition to your instance of interest J, right? And then think about the worst minimax risk you can get for any 2-point family. Now, usually I is going to be in a local neighborhood of J, but the definition as stated doesn't necessarily emphasize that. Okay. All right. So we've defined these notions of local minimax risk. What is the local minimax risk of policy evaluation? In the policy evaluation setting, everything turns out to be governed by this very simple matrix sigma star, which is a function of P and R. What does this measure? This measures the long-term discounted via the von Neumann series of this inverse matrix of the sample Bellman operator evaluated at V star. Okay, so this has a concrete operational interpretation, and it has a much longer expression just in terms of P and R in case you're interested. Once you have this functional, one can prove a non-asymptotic minimax lower bound for this problem. So the asymptotic version of this lower bound says that the minimax risk, when taken over the local neighborhood that I defined on the previous slide, the 1 over root n neighborhood, when you take n to infinity and then c to infinity, is given precisely by the expectation of a Gaussian, which is zero mean and has covariance sigma star. What's more, this is attained by the Polyak-Rupert averaged temporal difference learning algorithm. So in the asymptotic sense, we have a problem-specific notion of complexity, and it's attained by one of the algorithms we already described. This result builds on a bunch of work that's goes back many decades across optimization and local asymptotic normality and minimax theory from many decades ago. What happens in the non-asymptotic setting? Well, we can prove a 2-point lower bound that takes a very similar form. So for all sample size that's greater than discount complexity squared, the local minimax risk in the 2-point sense is actually lower bounded by the diagonal, the maximum diagonal entry of the same matrix. And it's easy to show that these two numbers, these two functionals, are within a logarithmic factor of d away from each other, right? So it's a very, very similar scaling of the risk in the non-asymptotic sense. And this gives us our baseline. Note, this is just a lower bound. We've not said anything about whether we achieve this baseline or not. Now, this, of course, leads us to the natural question of, does PR averaged temporal difference learning achieve this local minimax lower bound? In order to do this, we're actually going to consider a very simple instance or a class of instances for which we can evaluate this functional in a transparent way and actually make some plots to ask this question. So here's a simple sandbox. It's a two-state Markov reward process where the reward function here in red depends on the discount complexity or the discount factor gamma, and the P, the probability that you transition to this state, also depends on gamma. So everything here depends on gamma, and we have an additional parameter lambda that we can toggle. There's one absorbing state. So this is a nice little sandbox. As gamma goes to 1, this problem actually becomes one where the rewards are actually 0 on both of these states. The Markov chain also becomes disjoint and so on and so forth. So there's clearly varying degrees of difficulty that are generated just by moving a scalar parameter. Right, so the minimax risk that we evaluated before, the 2-point minimax risk, can actually be explicitly evaluated here, and it depends only on the discount complexity, 1 over 1 minus gamma to the power 1.5 minus lambda. All right, so now we have a lower bound, and now all we have to do is simulate the algorithms, for instance, Polyak-Rupert averaged temporal difference learning, to see if it achieves that lower bound. So let's set particular values of lambda and n, and run the simulation. The green curve here shows you the local asymptotic minimax, the local non-asymptotic minimax lower bound. And we've plotted the L infinity error against the discount complexity on a log-log scale. The other three curves are Polyak-Rupert average TD for different choices of the step size schedule. And as you can see just from looking at this plot, none of these algorithms actually adapts to intrinsic difficulty. This problem persists even if we change the values of lambda and n. We still have the slope of the lower bound being distinct from the slopes of these actual algorithms themselves. So what is this saying? Polyak-Rupert average TD is not instance optimal in the non-asymptotic sense, in finite samples, even though it is in asymptopia. Right? So going down and thinking about these local problems really helped us in the finite sample setup. So what algorithm is instance optimal in this setting? It turns out that a variance reduction device can save the day. Now, I don't have the time to talk about this in a bunch of detail, but the key idea here is to run the algorithm in epochs. And at every epoch, you recenter the stochastic approximation, iterate the standard TD, by some update that is supposed to reduce its variance. So in particular, T tilde is a near deterministic version of the stochastic operator, computed by taking many, many samples, say. And V bar is some recentering point. The closer it gets to V star, the more variance reduction you have, the better your algorithm gets. Right? So this is a natural algorithm to run in epochs, and it turns out that this variance reduction device shares similarities with many others in the standard stochastic optimization literature. So we were motivated to study variance reduction because Polyak-Rupert did not achieve the instance optimal lower bound. It turns out variance reduction does. If you run this algorithm for a suitable choice of step size and epochs, it turns out that its L infinity error is actually upper bounded by precisely that minimax lower bound functional you saw before, up to a root log factor. And this happens as soon as the sample size exceeds the discount complexity cubed. All right, so you can go back to the sandbox instead of just a theorem, actually look at how this does on those instances, the toy MRP, and you'll see that the L infinity error against the discount complexity plots look much like they did before. The local lower bound is strictly better than any of the PR averaged SA algorithms are able to attain, On the other hand, the variance-reduced TD algorithm now hugs this plot. So it's actually exhibiting instance-dependent adaptation at the optimal rate, as predicted by that green curve. A few words about the proof. Well, it's a fairly general-purpose proof. We have a generic decomposition where the variance of this variance reduction operator just sort of comes out and it matches the lower bound in a nice general-purpose way that might be of independent interest. Another thing that I should mention is that this is an L-infinity analysis, and in that sense, it doesn't, you don't have inner products and so on, which is very standard in stochastic optimization, so it requires quite a bit more care. So that concludes our vignette about estimation for policy evaluation. There are clearly some open problems here, and we'll talk about them at the end. But for now, let's just jump right into part 2 of the talk and ask if we can understand linear function approximation in this setting. So this is going to be a short part, and I will only sketch some results. So recall once again the policy evaluation problem. I mean, we've seen this enough now. There's a Markov reward process, P and R, a value function we'd like to estimate. And the function approximation setting is motivated by cases in which capital D, the number of states, is just huge. This is true in many modern problems in machine learning, for example. And what we'd like to do is approximate V star within the span of a set of basis vectors, little d of them. Okay, so this is linear function approximation for reinforcement learning. All of the standard algorithms for tabular reinforcement learning without function approximation, 3 of them, I just stated them again from before, they have concrete analogs in this setting, where you essentially involve a projection onto this subspace within the iterates of your algorithm. Now it's important to note that you don't simply take the original algorithm and project it onto the subspace. That's not how these algorithms are run. For instance, the plugin estimator is now the fixed point of a projected linear equation instead of just taking the plugin estimator and then projecting it onto that subspace, right? Concretely, this is also true for the others. Now I've written them in this slightly non-standard way to make the projections onto the subspace explicit, but really all of the operations you can carry out in little d dimensions, right? So effectively keeping track of those coefficients, and that's what makes them practical, interesting methods. Especially in cases where D is huge, the ambient dimension is huge, maybe even larger than your sample size. Right? That's going to be the setting of interest for us. So in this function approximation setting, there's the mix of approximation and estimation from a random sample. So what we would like is an estimate V hat of the value function that satisfies an oracle inequality of the following form, where you achieve an approximation error that's close, hopefully, to the smallest possible approximation error achievable, the closest point in the subspace to V star, up to a multiplicative factor alpha called the approximation factor. And then epsilon n is an additive term that models the interaction of noise, so the statistical error. So clearly we spent a lot of time discussing the statistical error in the previous part of the talk. This part of the talk will focus on the approximation factor. What is the smallest possible approximation factor that you can achieve for any instance, which is now given by PR and this subspace S. Right? So we'll ask this in the instance-dependent sense again. Okay, so let me just give you a short setting and summary of what we've shown. The settings, first of all, slightly different. So we'll have access to our simulator just like before, but we will access it by feeding it an initial state drawn from the stationary distribution of our Markov chain. So we won't just put in all states and get samples. The metric that we evaluate our error in is also going to change a little bit to a weighted L2 norm, weighted by the stationary distribution of the Markov chain. This turns out to be the natural one under which certain operators behave nicely. And the approximation factor, what's known about it? Well, Tsitsikris and Van Roy showed in their 1999 paper, it's a very celebrated paper, that temporal difference methods actually achieve an approximation factor that's like square root of discount complexity. So this is an upper bound on their approximation factor. Okay, so this already suggests something weird's going on here, perhaps different, where the approximation factor is no longer an absolute constant or unity like we usually see in non-parametric statistics. This is an approximation factor that's growing with some notion of dimension of the problem, in this case, square root of the discount complexity. But again, no lower bound was known. So what we show is that in these very high dimensional problems, if the ambient dimension is greater than the square of the sample size, then there is in fact a lower bound, which is instance specific on that approximation factor. So these are for very ill-posed problems, things where the dimension is greater than the square of the sample size. And in this particular f of p, r, and s is not unity. It's not even an absolute constant for many problems. So this is a very non-standard oracle inequality. At the same time, it's not always of the order 1 over 1 minus gamma square root. While this is a bound that can be achieved for certain classes of instances, for many others you can get significantly better approximation factors. Still not unity, but significantly better than this worst case scaling might suggest. Okay, so what's the main takeaway here? For these very large dimensional problems with function approximation, the approximation factor, the information theoretically optimal approximation factor is no longer an absolute constant. Okay? And while non-unit approximation factors are known in some of the literature, for instance, in density estimation, this approximation factor in the policy evaluation setting is not even an absolute constant. It's in fact much, much larger in many problems. So how do we establish this? We do this by actually establishing a more general result in a more general setting of projected fixed point equations, where you're interested in solving a system of linear equations of this form, general Hilbert space, where A is a linear operator. The only assumptions you need are that the operator norm of A is bounded suitably, and as before, you want an approximation to theta star in this case within a subspace S. So you have to make some noise assumptions, which are satisfied again by policy evaluation for various values of these constants. Basically, that the noise is well behaved along the particular basis vectors that you've chosen. So like we said before, this captures quite a few interesting settings. When A is 0 and you make some standard assumptions, this is just standard non-parametric regression. If you constrain B to lie within a set, we know that you can achieve the approximation factor 1 in this setting just by classical results going back to the 90s and the 2000s. But this is a general formulation. It captures policy evaluation, it captures Galerkin methods and numerical analysis, it captures a subclass of instrumental variable methods. So this is interesting in its own right. If the sample size is greater than the dimension, this is important, note that we can actually achieve an approximation factor 1, because all we can do is plug in the estimate, like we said before, and project that onto the subspace. This will achieve an approximation factor 1, and if capital N is much, much larger than capital D, the statistical error that we pay may not be that large. However, when the sample size is much smaller than the ambient dimension, what we'd really like to pay is the statistical error little d over n. Right? So we're interested in this ultra high dimensional setting, and that's the reason we end up paying for a much larger approximation factor. So under this larger, more general setting, what's the result here? Well, let phi of d denote some matrix formed by those basis vectors, phi 1 through phi d, and form this matrix M by projecting A along both of its dimensions using phi d. Now, alpha M is some instance-dependent approximation factor. It depends on M. It's the f of PRS that I talked about before. It's always upper bounded by the square root of the discount complexity, but in general, it depends on M. It depends on A. So when A is 0, for instance, you'd recover 1. And what we prove is a lower bound, right, for using this approximation factor or a lower bound of this approximation factor. So in order to do this, we need to define a local neighborhood. So how do we define our local neighborhood? It's all instances, all MRPs, such that the projection is exactly M, the M of the instance we care about. And the approximation error, how close you are to the subspace for the corresponding theta, is less than the approximation error of the instance you started with. This is, you fix a particular A comma B instance, that defines an M, it defines an approximation error delta, and that defines a local neighborhood. So our result is an information theoretic lower bound, provided the noise is sufficiently large and the ambient dimension is greater than the square of the sample size. The local minimax risk over this particular local neighborhood is greater than alpha of M times delta. So this is that multiplicative approximation factor plus the statistical error. So a couple of words about the proof technique. It uses the birthday paradox in the construction, which I find pretty cool and perhaps more general purpose for these approximation theoretic lower bounds. But it's a mix of these kinds of constructions with classical information theoretic techniques like Lecam's mixture versus mixture method, the Bayesian-Kramer-Rao lower bound, and so on. One thing I didn't get into, but I'll mention quickly, is that this bound is actually matched by a suitable temporal difference method up to higher order terms. So that concludes part 2, that the approximation error is also instance dependent and leads to a non-standard oracle inequality. This takes us to the takeaways of the entire talk. Clearly, the local perspective leads to multiple surprising conclusions, and I've illustrated 2 in this talk. We saw in the first part of the talk that temporal difference learning, even if you average the iterates, does not lead to instance-specific optimality in the non-asymptotic sense. And this motivated the development of a variance reduction device. From the approximation standpoint, we saw that in this problem, in the very high dimensional setting, there's a very non-standard oracle inequality that emerges. That probably is worth investigating in some more detail. Some things we didn't cover, but you can find in the papers, are that can you tell from the data if an instance is easy or hard? Can you evaluate these complexity measures from data? It turns out the answer is yes. We didn't cover the plugin estimator in any detail, or the TD lambda family of stochastic approximation algorithms and the Markov setting. We sort of stayed in the IIT setting. There are, of course, open problems that I said I would discuss, and here's a couple. They're ordered in sort of decreasing order of specificity. The first is that it would be nice to iron out these sample size dependencies. They don't quite match in all of our upper and lower bounds. This entire function approximation section was about linear function approximation projecting onto the linear span of a set of basis vectors. It's common now to use non-linear function approximation, neural networks, and so on. How do these things look like there? And throughout, we considered policy evaluation. So we considered a Bellman operator, which is really a linear operator. What if that operator itself is not linear? How do these things change? These questions are still well posed, but what are their answers? So I realized that was a bit of a whirlwind tour, but zooming out, I hope that I've convinced you that there are plenty of interesting questions at the intersection of high-dimensional statistics and optimal control. They're concretely motivated. They're important problems that call for moving beyond minimax theory and measuring adaptation in concrete senses. There's scope for independently interesting statistical contributions. So let me conclude by thanking my co-authors on these papers, Kaulik, Wenlong, Feng, Mike, and Martin. And the 4 papers you can find. The last one will be up on archive shortly. So thanks very much for your attention.